Tractors and dozers. Okay, so tractors and dozers. So remember that we have earlier looked at a few other types of equipment in which the dozers and tractors were not included. So now tractors and dozers are those equipment which are, for example, the tractor is equipped with a front mounted earth moving blade, and it is known as a dozer or bulldozer. Okay, so it is equipped with a front mounted earth moving blade. So a dozer moves earth by lowering the blade and cutting until a full blade load of the material is obtained. Then it then pushes the material across the ground surface to the required location. So this is the process for the dozer. So it cuts the material and then puts the material into its full blade, and then it pushes the material across the surface to the required location. So this is one picture of a dozer. As you can see that the blade also is on this side, and then with the power of this machine, this material is then pushed in the front direction. So crawler tractor dozer. So this is a crawler mounted tractor dozer. Okay. Another picture of a dozer. So it is a high-speed crawler dozer. So this dozer can move at a relatively higher speed. So this picture shows it very clearly that there is a front part of this machine which is called as the blade. It cuts this material out and then it pushes in front. So this schematic diagram of the dozer blades is like this. So the dozer blade has three types of motion: tilting, pitching, and angling. So tilting motion is, if you see from the front, then the motion in the clockwise or anti-clockwise direction for the blade is called as the tilting motion. If you see from the side, then the motion in the clockwise and anti-clockwise direction is called as the pitching motion. Whereas the angling motion is the rotation. Okay, is the rotation along a it is the rotation along a surface or along a curved surface of these front angles. That means if we, for example, if we look from the top side, so angling motion is we can see from the top. Okay, tilting motion from the front, pitching motion we can see from the side. So a motion we can of the motion of the blade of the dozer we can visualize from the three directions, from the top, front, and bottom. So then the motion, if take place like this, then due to this, these three types of motion, and provided with the enough power which is provided by the machine of the dozer can push the material out. Okay, so for the estimation of the dozer production, we have a few equations which we can consider. First equation is this 0.375 H times W times L. That is, if the blade load, that is the blade load of the dozer production, is equal to the 3 times H times W times L, where H, W, and HW and L are the height, width, and length of the dozer. And then this has to be multiplied by 0.375. So height, width, and the length of the dozer will correspond to the also to the direction of the correspond also to the dimensions of the cut that will be made by the dozer. There are also some fixed cycle times which needs to be considered. So these fixed cycle times are range from 0.05 to 0.15 of a minute. So depending on the operating conditions and the type of the dozer. So if the dozer is in a power shift transmission mode, then the cycle time is 0.05 minute. If it is in the direct drive transmission mode, it is in 0.1 minute, and in the hard digging, it is 0.15 minute. More data about the dozers is here in this table 4-5, table 5. Typical dozer operating speeds are range from the different types of actions which the dozer is operating. So for example, if the dozer is dozing, that is performing the cutting of the material and pushing the material in front, then it can have these typical speeds. So for example, if the materials are hard and then about 30 meter or less, then the speed will be 2.4 kilometer per hour. If the material is to be hauled, which is have to haul more than 100 feet, then the speed would relatively increase, to 3.2 kilometer per hour. In the loose material, so you can say take the speeds respectively for 30 meter or less than 30 meter or more than 30 meter haul distance to be 3.2 and 4 kilometer per hour. In the reverse direction, when the reverse is about 100 meter or less, in the reverse direction, the dozer is basically not pushing against some material. So the dozer is moving more or less freely. So it will be the maximum reverse speed in second range, that is in the power shift mode, or reverse speed in gear used in dozing, that is the direct drive mode. And similarly, for over 100 meter, it will be the maximum reverse speed in the third range, or highest reverse speed in the direct drive. So in the reverse range, the dozer speed will be relatively higher. So we can use these speeds and the other data to calculate the production level of the dozers. So let's see it with the help of the one example. A power shift crawler tractor has a rated blade capacity of so remember that both types of units have been given. So I have highlighted the data which will be used. We will be mainly using the SI units. So I have highlighted those units over here. So the rated blade capacity of the power shift crawler tractor is 7.65 loose cubic meter. This is the blade capacity. So the dozer is excavating loose common earth and pushing it a distance of about 61 meter. The maximum reverse speed is in third range is 8 kilometer per hour. So estimate the production of the dozer if the job efficiency is 50 minute per hour. So the production of the dozer will depend on the total estimate of the time as well. So for which we will, first of all, we will look for the fixed time, which will be 0.05 minute. So that has been given from this table because it is a power shift transmission dozer, it is 0.05 minute. And the dosing speed will be then 4 kilometer per hour. Why? Because the dosing distance is 61 meter, which is more than 30 meter. So if I see in the previous table, the dosing speed is more than 30 meter, it is 4 kilometer per hour. And then since it is dosing in a loose material, not in a hard material, so you can see that the dozer is excavating loose commoners more than 30 meters. So the dosing speed will be 4 kilometer per hour. So that means whenever it will push the material, then it will push the material at an average speed of about 4 kilometer per hour. So in that case, then since the dosing distance is 61 meter and the dosing speed is 4 kilometer per hour, so 61 meter divided by 4 kilometer per hour. So this will be the dosing time in hours. Since this 16.7 is the factor which we use, which we are using to convert the units, okay, to convert the units. So for example, the distance we have in terms of meters, the speed we have in terms of the kilometer per hour. Okay, so we want the answer in minutes. So if you will do all those calculations over here, so we will have to divide here by 16.7 minutes. So, so meter and then meter, kilometer per hour. So for example, if we convert meter into meter, that will be 1000 over here. And then per hour, in per hour, we have 60 minutes. So 1000 divided by 60. If you will divide 1000 divided by 60, so then we will get about 16.66667, something like this. So the approximate value is 16.7 over, we have been put over here. And then we get a dosing time of 0.91 minute. So in 0.91 minute dosing time, this 7.65 loose cubic meter of the material can be pushed forward. So here it is the explanation of this 16.7. So 1 kilometer per hour is equal to 16.7 minutes per meter. So this conversion of the units you can easily find out. So in the return time, so of course the distance is 61 meter, and the return speed will be 8 kilometer per hour. So why it is already given? Okay, the return speed is 8 kilometer per hour in the is given over here, maximum reverse speed. So 61 minute divided by 8, and then again we will divide it by this 16.7 minute factor. So the return speed will be 0.45 minutes. So now we can add up all these two times, the fixed time, dosing time, and the return time. So we get a cycle time of 1.41 minutes. So that means to complete one complete cycle for transferring this 7.65 minute loose cubic meter, we need about 1.41 minute. So that means if this cycle is repeated for 1 hour, that is, if this cycle is repeated for 1 hour, so the that means 7.65 minute divided by 7.65 loose cubic meter per 1.45. Okay, so that is the loose cubic meter per minute. Okay, and then in 1 hour the work is about 50 minutes, so we will multiply it by 50. So then we will get the answer of 271 loose cubic meter per hour. Okay, so 271 loose cubic meter per hour. So that means in 1 hour, this dozer can do a work of about 270 for moving that loose common earth, which is equivalent in quantity to about 271 cubic meter. But that moving of the earth job depends on the distance it has been moved. Now, if the distance is moved is greater than say 61 meter, maybe 100 meter, so then the answer will also change. Okay, so therefore, for various types of data, we can get different types of answers. So this was one of the way in which we can calculate the capacity of the in which we can estimate the production of the dozer. So the job efficiency means that means in 1 hour, on average, about 50 minutes of the work is being performed. So we have used this figure also before in other examples. Well, do you have any questions? Okay. Our next topic is about the loaders. So the similar type of machines can also work as the loaders as well. So this is over here, a loader has been shown over here. So a tractor equipped with a front end bucket is called a loader. Okay, front end loader or bucket loader. So this is the picture of a loader which is shown over here. So it is called as articulated wheel loader with articulated hauler. Another loader is shown over here. So this is a track loader. This is called as a track loader, or also we can call it as a crawler loader as well, because you can crawl. So the function of the loader is, as the name suggests, that it takes the material in and then it loads into some truck or some other place. So the function of the loader, main function of the loader, is not to cut through the material. For cutting through the material and then make the material loose and place it at some convenient location, we have the dozers. But from those dozers, some loaders can take the material and then load it into the different trucks. So they have different kinds of functions of these machines. Well, there is another loader over here. You can see that this loader performs two types of functions. It is a backhoe as well, and it is a loader as well. So the backhoe will cut through the material with this material, and the loader will load it. Okay, so it is a two-in-one loader over here. Another picture is about this skid steer loader with backhoe attachment. Okay, so this is a skid steer loader. That means this loader can work in the inclined, that is on the slopey fields very well. And then this is the compact. This is another loader. This is a compact track loader. So this track loader, you can see that it can work. It is more useful to work in muddy situations. because the soil over here was very soft. And then if we will use the wheeled loaders over here, if we will use the wheeled loader over here, then it may the loader may stuck into the soil. Another kind of loader, as you can see over here, this is called as a material handler. Okay, so it can handle the material on the side. So you can see that there are concrete blocks over here. These heavy concrete blocks. The stack of these heavy concrete blocks is being loaded it or unloaded. So of course the loaders can both load and unload the materials on the site. So without these machines, the work on the sites, on the construction sites, may not be possible. So heavy machinery is a requirement on the construction sites. Okay, so what are the cycle times of the loaders? The cycle times of the loaders can be taken from one of these few figures. So for example, for loose materials, for average materials, for hard materials, to be, and then depending on the whether it is a track loader or a articulated wheel loader. So the cycle times in terms of the minutes can be taken as these figures. So for the loose materials, if it is an articulated wheel loader, which is relatively slower than the track loaders, then it can be taken as 0.35 minutes. Okay, so one of the examples related to this is that estimate the hourly production in loose volume, LCY or LCM, of a 2.68 cubic meter wheel loader excavating sand and gravel, which is called as an average material, from a pit and moving it to a stockpile. The average haul distance is 61 meters. The effective grade is 6%. The bucket fill factor is 1, and the job efficiency is 50 minutes per hour. So here you can see that the bucket volume is 2.68 loose cubic meter. So the basic cycle time is 0.5 minute. Why? This is from table 4-6. So table 4-6, the basic cycle time is 0.5 minutes. So it is a, so you can see that it is what kind of loader is this? Estimate the hourly production in loose volume, wheel loader. Okay, it is a wheel loader in the average material, wheel loader in average material. So it is a wheel loader in average material. So the time is 0.5 minutes. Okay. Next is the travel time is 0.3 minutes. Travel time is 0.3 minutes. It is from figure 4-14. Figure 4-14. No, from here. It should be figure 4-15. So travel time is 0.4 minutes. So the travel time over here for the loaders can be estimated from this chart. So on the x-axis, it shows that one-way haul distance in feet and meters has been given, and then the different curves have been given for the slopes. Okay, so the slope is effective grade is 6%. Effective grade is 6%. So we will need to look at the 6% grade, and the average haul distance is 61 meters. So from here in this chart, if you will take this 61 meter, it will be somewhere here. And then about 200 meter, and then here we will get on 6% curve, we will get a value over here. And then on the, if you move towards the left side, so then we will get about 0.3 minute. Okay, 0.3 minute. So we will get a time of about 0.3 minute. Yeah. So the travel time is 0.3 minute. So in this case, the total travel time is given based. It is not like the time in one direction. So it is the time in both directions in this case, in the case of the loader. So the total cycle time in this case is 0.8 minute. So now if we say that if you take this 2.68 cubic meter divided by 0.8 minute multiplied by 50, so we will get its hourly production to be 168 loose cubic meter per hour. So therefore, I think this formula for the production you can use several times. Okay, so that means the formula is that the volume transferred in one cycle, we can divide it by the time of the cycle and then multiply with the efficiency. So that will give you the hourly production. So remember that the efficiency has to be given in terms of the number of minutes of work in 1 hour. Okay, so this formula can be used quite often in this topic, in these topics as well. So 168 loose cubic meter per hour will be the production in this case. So that was about the loaders. Again, a few more pictures for the loaders. So this is the different types of loader buckets, which has been shown. So some types of loader buckets have been placed with those sharp teeth as well, so that the material can be placed better well into the machine. Okay, so now another kind of materials which are called as the scrapers. Okay, so what do the scrapers do? Their operation and employment is based on this description. Scrapers are capable of excavating, hauling, and dumping material over a medium to long haul distance. So you can see that scrapers perform multiple type of works. So they can also excavate it, they can haul the material, and then they can also dump the material as well from over a medium to long haul distance. So if the job on the site requires these kinds of operations, so then scrapers can be used. So the scraper excavates or cuts by lowering the front edge of its ball into the soil. Okay, and then the ball front edge is equipped with the replaceable cutting blades, which may be straight, curved, or extended at center. So this is how the scraper is seen as working. So it is a twin engine all-wheel drive scraper. So this scraper is cutting the material out and then working it. So another picture of the scraper is over here. So it is the elevating scraper. Okay. Then you have the twin hitch scraper loading. Okay. So this is another kind of scraper. So normally when the scrapers are working, you will see that many machines working in different lines over here. So these are some of the working arrangements for these scrapers on the site. So there are also the pull scrapers, tandem pull scrapers as well. So the scraper estimation time scraper production can be also estimated with the help of a number of tables. So for example, this table 4-7 can be used for the fixed time estimation of the scrapers. So conditions has been given, the different types. These fixed time will also consist of the spot time, load time, and maneuver and the dump time as well. So these are different types of positions or the components of the processes for the scraper operation, in which we need to calculate the time. Okay, so how the scrapers work. So in this case of the scrapers can work in different types of modes. So one type of mode is called as the push loading. So here you can see that we in the how the scrapers are working. So for example, over here there is this there is a push tractor over here. This tractor is pushing, and over here there is a loading operation that is taking place, and then there is this scraper over here. Okay, and then that scraper is loaded, and then that scraper then is moved away, and then it goes to another direction, and then it performs the backtrack loading. And on the other hand, when this loading operation is going over here, and then that loading operation, when that loader has been loaded over here, and then it is then moved away from the location. So in this way, the push loading will work. But anyway, let's see one example. Estimate the production of a single engine 2-axle tractor scraper, whose travel time curves are shown in figure 4.4 and 4.5, based on the following information. Okay. So the maximum heaped volume is this, maximum payload is this, maximum material is sandy clay with this much, and material is sandy clay with 1898 loose density, bank density, loose density, and then the rolling resistance is this, job efficiency is this, operating conditions are average, and for the single pusher is the haul route is this, section 1 is this, section 2, section 3, section 4, section 5 is this, and then we have to find the solution. Okay, so a lot of data has been given, and then based on this given data, we have to calculate the production of this machine. So for this machine, first of all, let's look at the solution. So remember that we have to find the production. So production is nothing but the cubic meter per hour. So how many cubic meter per hour of the material this machine can transport, okay, and haul over some distance. So that we have to find. Okay, so first of all, we will calculate the load per cycle. So load per cycle will be 24 multiplied by 1,571. So 24 was the maximum heaped volume, okay, that this scraper can take, maximum heaped volume, and multiplied by 1,571, because 1,571 is the loose weight, okay? Loose weight per cubic meter. So 24 cubic meter divided by 1571, multiplied by 1571 kilogram per cubic meter. So that will be the weight in kilogram. That will be heaped capacity. So that means in one heaped capacity, the weight will be 37,794 kilogram. Weight exceeds rating payload of 34,020 kilogram. So the rated payload is 30,020 kilogram. Okay, so what has been said over here is the maximum payload is 34,020 kilogram. Okay, so the weight which we have calculated is 37,794 kilogram. So in this case, that means we will not take 37,794 kilogram. We can only take 34,020 kilogram. Okay, because of course we cannot put more than this amount. Okay, so this 34,020 kilogram will be divided by the 1898. What is 1898? 1898 is the bank cubic meter, density in the bank cubic meter, 1898 kilogram per bank cubic meter. So that will give us the 17.9 bank cubic meter per load. So in terms of the bank cubic meter per load. So here we are finding the calculation in terms of the natural state of the material. So that means how many cubic meter in the natural state we are carrying it. Okay, so the effective grade is -4 plus 50 by 10, which is equal to 1%. Okay, so how we have calculated it? Max effective grade is, so this is the Hall distance. Okay, so in the section 1 is level loading area. Okay, section 2 is down a 4% grade, okay, which is -4%, which is -4%, and then plus 50 by 100 is 50 by 10 is 50 by 10 is for it is the factor which is added for finding the effective grade. So 50 was no, 50 was what? So if we see that the formula before for the effective grade, okay, so we have to look at the formula. So what type of values are we are using over here? So the formula is, if we go back several slides before, the formula for the effective grade was we just discussed last time. The formula for the effective grade was this, yes, over here. So rolling resistance divided by 10. Okay, rolling resistance divided by, so if we will find the rolling resistance and then we divide by 10. So 50 was the rolling resistance in this case, so which is to be seen from a table from tables like this. Okay, so let me show it over here. So we were at this slide. Yeah, we are here. Yes, we are here. So it is 50 divided by 10. So this 50 has come from where? So the curves. So we will see the travel time curves for 4-4, figures 4-4 and 4-5. So estimate the production of a single engine 2-axle tractor scraper whose travel curves are shown in figure 4-4 and 4-. So we will go to figure 4-4 and 4-5. Figure 4-4 is here. Yes, this is the figure 4-4. Okay. So here you can see that, and then figure 4-5. So if we, I think maybe I can just copy these two slides and then bring it near there. Yeah. Okay. Yes, these two slides. Okay, these additional slides. So now let me see that. So here we have this. It is a 2-axle tractor scraper whose travel time curves are shown in figure 4-4 and 4-5. So let's see the travel time curves, figure 4-4 and 4-5. So this is figure 4-4. So scraper travel time curve in the loaded situation, and then scraper travel time in the empty situation. Okay. So in the loaded situation, what we have over here is this is the time in minutes, and then over there is the distance, one-way distance. Okay. So what we have over here is these are the travel time curves. So this we can use. So first, let's talk about the called the rolling resistance, which is over here. So it is the distance is 610 meter. Okay, and then the effective grade was found. It is equal to when rolling down, it was 50/10, and then the effective grade when the return was, it was 4%. It was 50/10. So over here we can see that in the section 4, it is up. Okay, or 610 meter. So suppose we have found this effective grade over here, then our next time what we are going to find is the for the turnaround time, it will be 0 plus 50/10. So the travel time will be then 1.02 meter from figure 4-4, and then the travel time from the section 4, which will be 1.6 minute. Okay, so how have we found the travel time 1.02 minute? So for this, we will look at this table. Okay, so over here, this is the loaded. So the distance is 600 meter. So 600 meter, and the slope was 1% slope. So if the slope was 1%, so that means we will see some value between here or between here and here. Okay, because 0 and 1%, 2%, this is the slope. So the travel time will be somewhere here. So it will be 0.8, and then this is about 1 minute. Okay, 0.8 and 1.2, this is about 1 minute value. So we can take a travel time of about 1.02 minute. Similarly, in the section 4, it is an empty situation. So we'll take it from figure 4-5. So this is the empty one, 600 meter, and the slope was, this value of the slope was 9% over here, right? 9%. So in figure 5, 600 meter, and then where is this 9% curve? 9% will be between these 8 and 9. So 600 meter and then somewhere here. So it is about, you can see that 1.2, 1.6. So it is about 1.4 something, more than 1.4 minute. So it is about 1.6 minute. Okay, it's about 1.6 minute. And in the section 5, what was the section 5? Section 5 was the turnaround section. Section 5 is the turnaround section. So in the turnaround section, we have found that the distance was 183 meter. So in the turnaround time, we have found that from figure 4-5, it is 0.45 minute. Why? Because in this case, the slope is, what is the effective slope is 5%. Effective slope is 5%. So now for the empty 600 meter over here, and then for a 5% value, so we can see somewhere some value over here. Here. 600 meter empty. Yeah, figure 4-5. But it is, the distance is not 600, it is 183 meters. So 183 meter will be somewhere here. So we will get a value something like about in this area about. So it will be more, little bit more than 0.4. So it can be taken it as 0.45 minutes. So we can add up all these times together. So the total cycle time is 3.07 minutes. So in terms of for the fixed cycle, so we will have to calculate these different times from table 4-7. So it will be 0.3 minute. So in this table 4-7, yeah, over here. So we will, first of all, we will have to calculate the spot time. So the material was average. Well, material is, yeah, operating conditions are average, okay, average, and single engine 2-axle tractor, okay? Single engine 2-axle tractor. So yeah, single pusher, okay, single engine, then the average condition is 0.3 minute, okay, and then this was the load time was 0.6 minute. Yeah, so the load time was 0.6 minute, and the maneuver and dump time was 0.7 minute. Maneuver and dump time is from figure 4-7, it is 0.7 single engine, and then so basically we can calculate these times from here. Okay, so now we have found out the fixed cycle time, which is 1.6 minutes. So fixed cycle time and the total cycle times both are added together. So it is 4.67 meters. So in that case, what now we have over here is, we have the bank cubic meter capacity was 17.9. We will divide it by 4.67 and then multiply it by 50. So in this way, we can see that this type of arrangement can produce 192 bank cubic meter per hour capacity. So again, you can see that although there is a lot of data which is given in this question, in this example, but everything is same, everything is connected over here, and we can use these data to calculate the hourly production of these equipment. So, so this is slightly detailed example of the scraper production. Example 4-9. Solve the problem of example 4-8 using the average speed method and the performance curves of figure 4-2. So if we will use the average speed method and the performance of figure 4-2, then the payload, as we have calculated in the previous case, it was 17.9 Weg cubic meter. And the effective grades were 1%, 9%, and 5% were there. But in this case, we will use figure 4-2 for the maximum speed, which were 52 km per hour, 26 km per hour, and 45 km per hour. So we will have to go back to figure 4-2. So what was figure 4-2 before? Yes, so this figure is also for the wheel scraper. So copy and then I will paste it over here. Okay, so yeah, now the figure is here. So the average speeds are 52 km per hour for hauling, and then 26 km per hour, and then the 45 km per hour. So that we can see from figure 4-2. So how we will see this? So for this, we will need to see the gross weight on the machine, and then we can read those values. Just give me a minute. Okay, so we can find this average speed factor from table 4-3, which is 0.74, and in the return it is 0.86, and in the turnaround it is 0.68. So in any way, then we can find this average speed to be 38, 22, and 31 kilometers respectively by multiplying those factors and by these average speed factors. So therefore, in this case, we can find the travel time in the haul to be 0.95 minute, return time to be 1.75 minute, and the turnaround time to be 1.75. So the total time will be 3.06 minutes. So we'll add it, the fixed time, which is given from example 4-8. And in this case, the estimated production will be also same. So either you choose the cycle, the timing approach, or the average speed approach, the answer is going to be same in both cases, almost same. Okay, there may be some differences, maybe plus minus 10% because we are looking at the values from the table from the chart. So we may read those values slightly differently. So, but more or less the answer will be the same. So the travel time curves of figure 4-4 and 4-5 assume acceleration from an initial velocity of 4 km per hour on leaving the cut and fill, and deceleration to 4 km per hour upon entering the cut and fill. So the results of adding together the travel time for the several sections will be because of an excessive allowance for acceleration and deceleration yield a travel time greater than the obtained by the use of the average speed method. So this time estimate obtained by the use of the average speed without speed method should be more realistic. So again, some some scraper operation has been shown over here. So this is called as the chain loading. Okay, so method. So in this case, as you can see that the loader moves to the other direction, and then one loader moves forward. And then another type of scraping operation is called as the shuttle loading. So I would recommend you to read the details of these operations from the textbook. Then it will be much clear as well. Then we have for the scraper the optimum load time. So this chart shows the load growth curve. So the optimum load time. So as you can see that as the time increases, the optimum load time, as the time increases, the optimum load of the scraper also reaches to some almost maximum value. So more loading than the given time may not be very beneficial for the operations of the scraper. So another chart for the calculation of the scraper's load time is also given like this. So you can use this chart to calculate the cycle time for the loader, cycle time for the scrapers as well. So also for the scrapers, the number of pushers required can be calculated by these relationships. Using these equations and the table 4-8, which gives like typical pusher cycle time for the backtrap and the chain or shuttle type of. So see with this, we can see the example 4-10. So the estimated cycle time for a wheel scraper is 66.5 minutes. We calculate the number of pushers required to serve a fleet of 9 scrapers using a single pusher. So calculate the number of pushers required to serve a fleet of 9 scrapers using single pushers. So determine the result of both backtrack and chain loading methods. So number of scrapers per pusher is equal to the backtrack time, which is 6.5 divided by 1.5. So 6.5 minutes divided by 1.5. So if you use this equation 4-11, so 6.5 is the scraper cycle time, pushers per cycle, which are that is 6.5. The estimated cycle time for a wheel scraper is 6.5 minutes. Okay. Calculate the number of pushers required to serve a fleet of 9 scrapers using single pusher. So determine the result of both backtrack and chain loading methods. So this 1.5 is from here. So for the single pusher, the typical pusher cycle time is 1.5 minutes for a backtrack. Okay, and then for for the chain, it will be 1. So the number of pushers then required are then we can use these values. 9 divided by 4.3 for the backtrack are 3. That is, we will that means we will get a value of 2.1. Then, but we will just make it a whole number. Okay, and in the chain, it will be 2 in this case from equation 4-12. Example 4-11. So find the expected production of the scraper fleet of example 4-10 if only one pusher is available and the chain loading method is used. So expected production of a single scraper as assuming adequate pusher support is 173 bank cubic meter per hour. So as it can be seen that the number of pushers required to fully serve the fleet are equal to 1.4. Okay. So in this case, we can calculate the production as 9 into 173, which is the volume. 9 are the number of scrapers, and then we will divide it by 1.4. So we will get, in this case, about the capacity of about 1,112 bank cubic meters for those 9 scrapers in the line. Okay, so after this scraper, then we have this topic of trucks and wagons. So the operation and the employment of the trucks and wagon is quite self-explanatory. Trucks and wagons are still the most common form of construction hauling equipment. The heavy-duty rear dump truck is most widely used because of its flexibility of use and the ability of highway models to move rapidly between job sites. So this is a 40-ton truck rear dump trunk has been shown over here. So as you can see that trucks are very common construction equipment, and they can be used to transport material from one location to another location in a much efficient way. So here you can see that there is this bottom dump wagon. Okay, and then how we can determine their trucks and determine the number of haul units needed. So for this, we can use this table. So bottom dump truck and the rear dump truck, and then gives us the spot maneuver and dump time for the trucks and the wagons in terms of the minutes. So this table makes the calculation for the truck relatively simple. So for example, the loading time will be what will be the haul unit capacity divided by the loader production at 100% efficiency. That will be the loading time. So loading time can also be calculated by the number of bucket loads multiplied by the excavator cycle time. Or another equation will be the number of hauler required will be the haul unit cycle times divided by the loading time. And the expected production is equal to the actual number of units divided by the n, equal to excavator production. Well, these equations are of course given over here, but they are more or less depend on the job conditions, and then we can apply these equations intuitively when we are going to solve the questions. So as an example, we can see that given the following information on a shovel truck operation, calculate the number of trucks theoretically required and the production of this combination. Calculate the expected production if 2 trucks are removed from the fleet. So shovel truck, the data given is that the shovel, which is an excavating machine, and just assume that it is performing at 100% efficiency. It is producing 283 bank cubic meter per hour. The job efficiency is 0.75. The truck capacity is 15.3 bank cubic meter per hour. So that means if a shovel is producing 283, so in order to match this 283, we will need a number of trucks. So the truck cycle time will be the 0.45 hours. So this is a simple operation over here. For example, over here, the loading time of the truck will be 15.3, we have to load. And then 15.3 divided by 283. So that is the 283. So that means for the loading time, that means if we need to load the truck, then it should be 15.3 divided by 283. So this is one of the approach for calculating the loading time, so which is given to be 0.05 hour. However, in order to match this capacity, we will need to find out how many trucks we will be needing. So the truck cycle time will be 0.5 plus 0.054. So 0.5 minute will be the truck cycle time. That means truck goes to the unloading position and then comes back, excluding the loading. So for the loading, it will be 0.05 hours. So the truck cycle time will be 0.55 hours. Okay, so the number of trucks will be needed will be in that situation will be, because the truck cycle time is 0.55 hour, and then in one load 0.05 hours are needed. So therefore we will need 10.3 trucks. 10.3 divided will be in whole numbers, it will be 11 trucks. So the expected production in that case will be, because we will be meeting that 283 bank cubic meter shovel production with those 11 trucks. That means we will need 11 trucks that will meet this 283 bank cubic meter production. Multiplied by 0.7, that is the job efficiency. So expected production in this case will be 212 bank cubic meter per hour. 212 bank cubic meter per hour. But this is not just because of the shovel. With this shovel, we will need 11 trucks of this capacity. But if we have 9 trucks over here, so the expected production will then decrease. So from 212 to it will decrease to by 9, because we were actually needing 10.3. So it will be decreased by a production of 9 divided by 10.3. So it will decrease to 186 bank cubic meter per hour. Okay. So although we will be using the 11 trucks, but for the calculation of the decreased production, we will be using the this fractional number over here to decrease the production. So the production in this case will be 186 bank cubic meter per hour. So in those situations, the shovel will also have to decrease their production so that to match the production of the trucks. So if we have less than 11 number of trucks, so the production will decrease. If we will have more than 11 number of trucks, the production will not increase, because the production will be limited by the production of the shovel. Okay, so with this, we have completed this topic. Okay. And then on Thursday, we will start another topic, which will be the topic number 9. So in fact, we have left with 2 topics in this course. Okay, so are you here?
Yeah.
Yeah. So if I see these over here, later on, I will also give some assignment and the practice questions as well. So earth moving materials and operations has been completed, and then today we completed the loading and hauling equipment operations. So now we have left with 2 topics: compacting and finishing equipment or operations, and the concrete formwork. So in the remaining time, we will complete these 2 topics. Okay. Well, any questions?
No.
No questions. Why?
I think it's clear.
Clear. Okay. Is it clear? Okay, I don't think so. It will be more clear, I think, if you will follow along and then once you will do some more practice questions, then it will be more clear.
Okay.
All right. Okay, then that's all for today. So I shall see you on Thursday. Bye-bye.
Yeah, goodbye.